So the car performance, speed versus motor current. This is a rough graph of what happened in the 0305 car with motor current coming in and speed on a flat, no headwind, not uphill, not downhill for it. So you can see what happens. You've got the aerodynamic drag coming in. That's actually the power required for aerodynamic drag. This is in power, is actually a cubic function. The rolling resistance. Now aerodynamic drag, I'm not taking into account, I'm sort of taking into account the wheel well waffles and everything else in here for these numbers. We'll see an equation for sort of just a pure aerodynamic drag in a second. But this is something that's sort of the whole shot. Somewhere around 40 miles an hour, the aerodynamic drag and the rolling resistance for that car are the same. Where do you think it crosses with your current car? I have no idea. Why? Never driven it like that. Yeah, I got no idea. Is it 30? Is it 70? I don't know. Now, why do I know this? Well, we collected data and we wrote it through complete races. So I got some numbers I pretty much know coming on here. But what does that say? Now, what would the energy be for both of these? If I add them together, that would be it. What's the energy doing? It's going up cubically as speed goes up. So, that's not necessarily a good thing, right? The faster you go, the more energy it takes. You've got a limited energy budget, so part of it is strategy. So what happens if you don't have strategy and don't have data, and you start driving the stroller car and you say, well, it's 8 o'clock in the morning, looks like we've got a full battery pack, let's go what? 60 miles an hour, let's hammer, man.
So
of course.
10 o'clock?
2 o'clock. And you got 3 more hours a day to go, and you got 0 in the battery, so what do you got to do?
You sit there and you burn time?
You just sit there until it's time to close, and then you say, we didn't get quite as far.
Trailer in.
Yeah. Well, in the middle of the day, you trailer, the old races that were longer, you picked up and you went back to where you started in. But yeah, if you didn't make it to the stop because of it, and it's a stop you have to reach, you trailer. So if you run out of power, you do that. So here's a couple numbers from that graph. Only given the losses on the last slide, none of the other losses we've got. How can you go on 48 amp hours of power? Not really power, but well, somebody that's constant voltage, so that's high power. Since those were in amps in it. At 40 miles an hour, you go for 4 hours. That's 160 miles. At 60 miles an hour, just 20 miles an hour faster, you can only go for 1.64 hours or 98 miles. So, if you've got to reach a waypoint 160 miles away, what do you want to do? Run 40 miles, or you got 4 hours to do it, or do you want to try to go faster, run 60 miles? Yeah, you ain't going to make it. Yeah. So, that's why strategy and knowing something about your car is critical. Driving faster is not usually a winning strategy. It's a loser strategy. It's the testosterone-driven, let's go, let's chase them, let's get them, let's get ahead of them. I don't want to get ahead of them during the day. I want to be what?
Ahead of them when you start the next day.
Yeah, at the end of the race. That also means if I know it's cloudy the next day, and the weather says it's going to be bad, I might want to leave what?
Some energy in the battery.
Some energy in the battery pack for tomorrow, so I can actually run at a slower speed, but can run longer, where everybody else is going, we didn't save any power. Okay? So, strategy, knowing all those things is critical. Okay, let's just talk a little bit about some of the aerodynamic performance. Here's a car. The front edge of a car there. What happens when you run the front end of a car into the wind?
It has to split the airstream.
Splits it, and if you're lucky, what does the airstream do along the surface?
Flows.
Yeah, well, what's the right word? Laminar. Laminar flow. Yeah, it means it flows right along with it, which means there's very low resistance on that. And then at a certain point, about the time your array starts, and it gets a little rough, or even if it's smooth after a while, you get separation and turbulence. That's where the drag is. There are some things you can do to reduce that, and jets and other things, but But you concentrate on having a nose and going ideally 8 inches back at least, and having that as smooth as possible, polished, Same thing on the sides. Even those decals ought to be, not decals sticking up, they should be smooth. Same thing happens with the what? At the top. Canopy. It's going to be going down. You want it to grade, you want sort of a bubble shape in the front, as smooth as you can get it. No cracks, no wrinkles, no strange stuff in there, smooth. And then tapering back. Yeah, teardrop. Well, kind of. And if you do the right shape on here, you can get it to be laminar flow quite a ways back. And you can even do things like put a little row of sandpaper around here at the right place. It'll take that separation boundary layer, create a little turbulence, and cause some reattachment. But you have to know what you're doing. You have to test it. You have to take it out on the road where you got little smoke things going over it. You watch it, you say, where's the separation? Where do I try this? Put that stuff on there, then see what happens the next time. But it can make a dramatic effect, not just small effects. Here at the end, what do you think this tail end should be like? Knife edge. As narrow as you can possibly make it. Okay, 1 centimeter, probably wider than you want it. Now why? Because when you go off a blunt end, what happens? Turbulence. You start getting these eddies, and what does that create? It's like a vacuum that's sucking you back. And you can test for that going down the street. If you have a little bit of smoke coming down or dust coming out of it, you can see the actual eddies. There's two types. There's the type that curls in because you don't have a knife edge, and then at the corners, sometimes you see vortices. They're vortex elimination things that people sometimes will put at the corners to try to prevent that from happening.
Stanford had those on the top of their
But you want to test it, because if you're not testing it, you might put on something that actually makes it worse. It's tough to do without testing and doing it. So aerodynamics people, wheels, wheel wells. Oh, wheel well turbulence and putting fairings in. Of course, if you put a big fairing in that goes way, way back over there, what happens when you get a little bit of side wind?
It pushes the car.
Well, yeah, you've got a bigger frontal area then. Here's the general equation for power coming in. It's 1/2 rho, that's density of air. So when air is denser, your power goes up. When humidity is high, is air denser or lighter?
Denser, you have the water.
I think so?
Lower.
Is density lower or higher?
Is it fog or is it?
No, just humidity.
If
No
it's
fog.
humidity, it's lower.
Humidity, it's actually lower because
Water is less.
H2O is lighter than
Yeah.
nitrogen and all that other stuff in the air. So it actually gets better if the humidity's a little higher. Strange. Not condensing humidity, not rain. Cool. Okay, anyway, you've got that, and of course when you're at higher elevation, it goes down. And this is actually a significant enough effect that you want to actually model it in your model. You want to know what's the current air pressure, what's the current temperature, air pressure and temperature, and what's the current humidity to come up with a model for that. V cubed. As velocity goes up, the power required goes up cubically. A, the frontal area, that's projection of frontal area in the car. And CD is a drag coefficient. In other words, what that means is your car shape has a certain CD for it. And if you double the frontal area, you're going to double the drag. So the CD is for the shape, the A is for what's in there. That doesn't take into account the wheel wells, doesn't take into account air leaking in and out and other things. Okay, rolling resistance. What is rolling resistance primarily?
The resistance between the wheel and the
Yeah, it's going to be the losses in the wheel. Why do you have losses in wheels and tires? They're flexing, right? They're flexing, just flexing. The bottom part is compressed, the top part's not. It flexes, it moves in it. And you've got that. You've also got one other loss. Where's the other loss? Bearings. Of course, in our car, we've got a third loss. What's the big third loss I've seen in your current car? Well, that would be aerodynamic, right? I'm talking about rolling resistance.
weight,
Brake drag.
parking brake.
Brake drag.
Brake drag.
Okay, you need to try to minimize that as best you can. Yeah, that was dramatic. Okay, well here's the equation that sort of models it. It's near linear. W here is the weight of the car. W is weight of the car, not mass of the car, weight of the car. What does that say? That says, if we look back at the amount of energy it takes for the car, it's linear. on weight on the bearings and on the tires. It's linear in weight, so you've got to reduce the weight of the car. And up until 40 miles an hour, that's where aerodynamics and approximately, at least for the last car, and rolling resistance were equal. Okay, so half of your car speed, your power at 40 miles an hour, plus or minus, is weight of the car. I usually do these things in what units myself? Metric, but I'm talking to you in English. When I code things, they're all coded in, metric units coming in, and the driver displays and things, that's where the translation happens. It's easier to keep things right. Otherwise, we'll be crashing Mars instead of gently landing on it, right? Yeah. Don't, if you're coding something, I suggest, pick the MKS units, do it that, and only if you need the input-output something else, convert it. Don't mix inside. But if half of our power at 40 miles an hour is approximately, that's about where the trade-off is. If that's going to be rolling resistance, and rolling resistance is dependent on weight, and the 0305 car weighs 200 pounds less than the current car, in other words, 2/3 of the weight, it's going to require about 2/3 of the power on rolling resistance, or you're going to be saving 1/3 of your power coming in. So weight is critical. That's why you try to reduce weight on everything you do. Solar car performance, air leaks. All right, suppose you have air leaking into the car. Hole in the front. Hole in the wheel wells where it comes in the front, goes out the back. Okay? Ventilation even. Any air in and out. What happens? Well, the main loss, there are other turbulence questions and stuff too, but the main loss, one big loss, is you have to take that mass of air coming in, let's assume it's at 0 miles an hour, and you have to speed it up to the car speed. You have to accelerate it. And then when it goes out, when it goes out, it does what? Hey, Sam was now. You have to deaccelerate it. That takes energy. That takes power coming in. The kinetic energy is 2 times 1/2 mv squared, where m is the mass of the air you have to accelerate and deaccelerate. V is the velocity of the car, assuming everything's flat. Oh, wait a minute. Let's go back a second. Oh, here, aerodynamic drag. This V spewed an aerodynamic drag. That assumes the air is running what?
Over the surface of the car?
No, the ambient air is what? 0, and that's the velocity of the car, right?
No.
What if you're going 40 miles an hour and you got a 20-mile-an-hour headwind? Yeah, this V is 60 then. So then we move back up to where on that chart? Whoa, way up there. So headwinds, you have to adjust for that. You got to make that clear. That V was that V back there was relative speed, not the absolute speed. Okay, back here. That's why if you have a headwind, you've got to do what? Slow down. Treat it as though you're having to drive faster. It doesn't hurt the rolling resistance, but it does greatly increase the aerodynamic drag and power loss there. Okay, anyway, roughly at 60 miles an hour, typical atmospheric density about 1.2 kilograms per cubic meter. If you have a 100-centimeter hole, square hole, do you think your holes in your wheel wells and the cracks around the array, do you think that adds up to 100 square centimeters in your car right now, or more?
Yes, more.
A lot more. More. This would be a tight fit. This would be tight. Your car ain't tight. Okay, if it was tight then, you're going to have a loss of about 8.5 watts. Your car is probably 10 times that right now, maybe. So, what does that say you need to do? If you're really going to race, you want to tape that array shut, make it smooth, just have the driver so he can exit. But you also need to have closed wheel wells so you don't have air going in and out. And as small holes inside the wheel wells as possible for that extra turbulence. This isn't even the turbulence in wheel well. This is just the acceleration and deacceleration.